Hi, I'm Matt, and in this video we're going to go over what equilibrium is and three main types of equilibrium that you have to know. Before we can get into what equilibrium is, we have to go over a reversible reaction and what they are. So a reversible reaction is a reaction that creates products, but also goes backwards to create reactants as well. We call this creation of products the forward reaction, and the creation of reactants the reverse reaction. When we get to equilibrium with a reversible reaction, we're going to get a mix of products and reactants. We won't get all of one or all of the other. Now that we know what a reversible reaction is, we can start talking about equilibrium. So, at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. In other words, the rate or the speed at which we make products is the same as the rate at which we are making reactants. Since the rates are the same, the amount of reactants and products will stay constant. The amount of reactants won't change, and the amount of products won't change. Keep in mind that these are not necessarily equal, just that they are constant. And equilibrium is dynamic. Equilibrium is dependent on external factors such as temperature and pressure. So at different temperatures, we might get a different ratio of products to reactants. Now, there are different types of equilibrium. In this video, we're going to go over three main types: phase equilibrium, solution equilibrium, and chemical equilibrium. So the first type of equilibrium we are going to discuss is phase equilibrium. This is when we have two phases, just as a solid or a liquid, present at the same time in a system, and their concentrations aren't changing. For this to occur, we must be at our melting or boiling point, because otherwise the reaction won't be reversible and we'll end up with all one phase. And lastly, the system must be closed to prevent any vapor from escaping. So, an example of this is having 10 grams of ice in 30 milliliters of water in a stoppered flask at 0 degrees Celsius and 1 atmosphere. So, 0 degrees Celsius and 1 atmosphere is the melting point of water, so we got that checked. The flask is stoppered, so the system is closed, so that's correct. And as long as our 10 grams of ice and 30 milliliters of water, as long as those numbers aren't changing, we are at equilibrium. So, we could say here that the rate of melting equals the rate of solidification, where the rate that the solid becomes the liquid is the same as the rate in which the liquid is becoming the solid. So here is just an image of phase equilibrium. I did my best to draw a stopper on the top, but pretend it's stoppered. And then we see that we have the ice block and a certain amount of water. If this system's at equilibrium, that ice block will not change in size, and the amount of water will not increase or decrease. The second type of equilibrium that we are going to discuss is solution equilibrium. There's a few terms with solutions that we have to define, but we'll go through those as we get to them. So, at solution equilibrium, the rate of dissolution equals the rate of precipitation. So, dissolution is when a solid breaks up into ions and dissolves into the solution. Precipitation is when ions come together and form a solid that comes out of the solution and sits on the bottom. So, when salt dissolves in water, that's the dissolution. And if we add too much salt and we get solid at the bottom, that's precipitation. Now, for solution equilibrium to occur, the solution must be saturated. That means that no more of that solid could be dissolved. Such as with salt water, if we keep adding salt, eventually no more salt will dissolve, and it will just sit on the bottom of the flask or beaker or whatever it's in. Continuing on with solution equilibrium, the amount of the precipitate or the solid at the bottom and the amount of dissolved particles stays the same. So for example, in a beaker that is a saturated NaCl or just salt solution with 30 grams of salt undissolved at the bottom and 38.4 grams dissolved in the water, the amount of particles dissolved and the amount of particles undissolved remains the same. So we will always have 30 grams of NaCl undissolved at the bottom and 38.4 grams dissolved in the water. At the bottom there, that's just the equation for the dissolution of NaCl, and that double-headed arrows means equilibrium. Here's an example of that from the last slide. So you see we have one piece of solid NaCl on the bottom, and then we have 3 Na plus ions and 3 Cl minus ions dissolved in the solution. No matter what happens, unless we add more salt, we will always have those 6 dissolved ions and the 1 undissolved solid. Now, 2 of those ions could come together and form a solid, and that solid on the bottom dissolves, but that in the end will not change how many we have in total. They will just swap places, for lack of a better term. The last type of equilibrium we are going to discuss is chemical equilibrium. Now, this is a chemical change instead of a physical change. Remember how dissolving something and phase changes are physical changes. Here, when the reaction occurs, we're going to get a new species produced. So here I just have a sample reaction. 2 hydrogen, or H2, plus I2 will make 2 HI particles. And you see those double-headed arrows mean we're at equilibrium. And just like always with equilibrium, the rate of the forward reaction is going to equal the rate of the reverse reaction, and the concentrations are still constant. Even though there's a chemical change, what equilibrium means here doesn't change. So here's what's occurring at the particulate level. Here we can see we have 2 gaseous H2 molecules and 2 gaseous I2 molecules, and then 1 gaseous HI molecule. No matter what happens, these concentrations will remain constant unless we add more of the species, or we could change the temperature. Now, it's not to say that HI and I2 won't come together to make an HI, and that an HI won't split up into H2 and I2, but the concentrations will always stay the same. Now that we've gone over what equilibrium is and the 3 different types of it, here are 5 practice questions to test your understanding. I encourage you to pause the video at this time and try them on your own. The solutions will be provided for you on the next slide. The answers are as follows. The rate of the forward reaction and the rate of the reverse reaction must be equal at equilibrium. The amount of products and reactants must stay constant at equilibrium. Not equal, constant. For question 3, the rate of vaporization, or the rate at which something becomes a gas, has to equal the rate of condensation, the rate at which that gas becomes a liquid. And at 4, the system is at equilibrium because the concentrations do not have to be equal, just the rates. And 5 is not at equilibrium because the rate of the forward reaction does not equal the rate of the reverse reaction. Hopefully you got these. If not, feel free to leave a comment below with any questions you might have, and I will get back to you as quickly as possible. Thank you so much for watching, and have a great day.